know, which is virtual again this year. It's September 17th to the 19th. So if you are interested in joining the event, please make sure to go on to our website, didaconla.com, to get more updates and information. In addition to the tutorials and regular tracks with sessions, we're also going to do a startup showcase as well as a product hackathon. So please make sure to follow. There's currently a 50% discount for students. The code is on the website. It's $20 regular and $10 for students. With that, I just want to again thank Dr. Sultan for hosting this talk. And today we have Dr. Sultan from the Cal State LA, who will be talking on smart grid benefits from energy storage. Dr. Sultan, you want to take it over?
Yes, thanks, Sabash. It's good to see everyone. Hope you all have stayed safe and healthy since we last met. For those of you who do not know me, I'm Vivian Sultan, a business faculty at California State University. It's 5:30 p.m. on May 5th. Happy Cinco de Mayo. And I'm hosting this webinar for DataCon LA. A little bit about me. I live in Glendale, California. My PhD and previous research focus is in energy informatics with the emphasis on smart grid reliability. The intent of this session is to discuss energy storage and how it will play an important role in improving the reliability and the operating capabilities of the electric power network. This material is prepared as part of my current research work to provide actionable information for the state, developers, the electric utilities, and other stakeholders who are concerned about the reliability of the electric power network. This is the agenda. I will start by giving you an introduction about energy informatics. Then we will discuss a taxonomy of battery storage grid operating benefits. We will chat about grid reliability and power quality, which is the main focus of the session. Then we will examine how battery storage will improve transmission and distribution. In the fourth section, we will go into how battery storage will facilitate renewable and intermittent generation. The last section is about energy storage as an enabling technology to offer faster grid responses. At the end, we will recap and we'll discuss the lessons learned. The purpose of this first slide, and you have probably seen this slide from my previous webinars and presentations, is to give you a brief introduction about my research and what I do. So I'm in the energy informatics research domain, which is the research field that covers the application of information technology to address challenges and resolve problems within the energy domain. Christophe Goebel from Berkeley was the first one who came up with a framework for the energy informatic research in year 2014. In 2018, I introduced this enhanced framework to include service reliability as a separate research movement, considering the significance of the theme in the modern grid design and the current grid reliability challenges that are facing the electric utilities. So if you look at this framework in the image, you can see that research movement are classified into three main types: energy efficiency, renewable energy supply, and the reliability theme. For those of you who are not from the utility industry or who are new to the industry, energy efficiency is the research goal that drives the evolution of smart energy saving systems. It's about studying the incentives and the dynamics that influence the usage behavior of the electricity consumers. The second type of research, renewable energy supply, involves resolving challenges that arise with the integration of renewable energy resources into the grid. It's about the advancement of the smart grid, and finally the service reliability, the third theme. That is the theme that I'm going to talk about today, and what I have always been interested in. In my research, the emphasis has always been on the spatial distribution of distributed energy resources and resolving grid integration challenges to ensure service or grid reliability. We can start by making a statement that energy storage technologies present a number of operating benefits to the grid. There are 4 classes of benefits in this figure that I developed to summarize the core concepts of today's session. One is improving grid reliability and power quality. And in this section, we will talk about load following, regulation up and down, operating reserves, spinning and non-spinning reserves, peak shaving, voltage regulations, and droop control. The second class of benefits is about how the battery storage will improve transmission and distribution. And in this section, we will discuss battery value for decreased transmission losses and reduced transmission congestion. We will also define the concept of islanding and how batteries can allow portions of a network to function as an island power system. In the third section, we will talk about how battery storage will facilitate renewable intermittent generation by meeting renewable portfolio standards and lowering carbon footprint. The final and the fourth class of benefits is that energy storage is looked at as an enabling technology necessary in the smart grid environment. We will talk about how energy storage may allow faster grid responses. So what is the grid reliability is about? In simple words, it's the ability of the electric power network to deliver electricity without any degradation or failure. Do we need to talk about it? Yes, and I have mentioned that in all my previous talks in the industry. I think we definitely need to talk about it, especially with all the grid reliability challenges that we have experienced in the last couple of years. Another point is that we are making so many changes to the electric grid, the widespread deployment of renewables and the addition of new components all justify why we need to talk about grid reliability. So the electric grid is evolving from a one-way power flow system where electricity generation was kind of centralized to a smart grid that allows two-way power flow and the incorporation of the various types of DERs. We are moving to the distributed generation system. This is an EPRI slide that I really like, and EPRI stands for the Electric Power Research Institute. It shows you how the electric grid is evolving. We are transforming the electric power system to allow the two-way power flow and the incorporation of the various types of DERs. We can claim that it's a paradigm shift or a revolution. So knowing that reliability and revolution do not go well together, we need to talk about reliability and the new technologies such as battery storage that will be effective tools in managing the reliability of the electric power network. Again, this is from my previous work in the domain. This is a framework that I developed to help us understand the reliability issues or key challenges on the network side. This was based on a broad automated search using 2 digital libraries. If you look at the image, you can tell that there are three main types of reliability challenges. One, hardware and electric and technical failure. Two, environmental related. Three, operational related failures. I broke those challenges further so that you can go through them. If we look at the recent reliability issues in California, for example, you will see that we have a mix of two or more causes of outages. In the last few months or the last year or so, we have seen outages that fell under the PSPS work, the public safety planned outage bucket, the wildfire, the heat wave in California. In other states, we have also seen the ice storm in Texas. So these are mainly environmental related outages. And we have also seen operational related failures due to inadequate capacity or power supply shortages. In the reliability research framework that you see in this image, the operational related failures fall under the bulk power system research focus. And that is why the effects of this outage can be felt in more than one location on the network. Reliability of power supply and system operation, regular evaluation of expected or emerging changes, and system maintenance are all possible goals of researchers who work on the bulk power system side. So we can agree that the grid reliability is the greatest concern facing electric utilities. We are all feeling and living this concern. Within the utility industry, all the PSPS work that has been done, the recent outage events that hit Kaizu grid last year, and the current outages, and also the outages that we have seen in Texas. It's a good time to talk about battery storage, since it is that critical component or effective tool to be added to the electric power network, and that is expected to contribute a lot to the overall system reliability. We can start by making a statement that energy storage can reduce the overall system variability, shift load time, and control ramping time simply by providing redundancy options, for example, in areas with limited transmission capacity. Energy storage system can provide VARs, and VARs stand for volt amperes reactive. It is that unit of reactive power to quickly increase and maintain voltage in periods where when large amount of loads come online. Energy storage offers services such as load following, so it acts as a resource that adjusts its power output as demand for electricity fluctuates throughout the day. It serves as a spinning reserve because its output can be ramped up and down in response to changes in demand. This support could be very helpful in preventing voltage degradation and potential system collapse. I just want to bring it to your attention that voltage stability problems are usually caused by unplanned tripping of generation and/or sudden loss of load. Another important point is that the converter systems associated with energy storage devices can also provide power quality benefits by acting like a system filter and eliminating unwanted variations in both frequency and voltage. And for those of you who are not electrical engineers, voltage is about the electrical physical quantity, while frequency is about the oscillation between the positive and the negative voltage. So if there is a more demand for electricity than there is a supply, then frequency will fall. And if there is too much supply, frequency will rise. Power frequency that go 1% above or below the standard may risk damaging equipment and infrastructure. Final point that I want to make here is about drop control, which is a popular way to regulate the frequency by adjusting the output power of a controlled assets, such as a generator, or in this case, a battery. In a drop mode, the battery output and the frequency are inversely proportional. When frequency decreases, power output from battery increases, and vice versa when frequency increases. To make a long story short, integration of energy storage systems into the smart grid can manage the power variability of renewable generation by providing ramp rate variation control and frequency regulation via drop control response. If you look at this table on the right, this is a taxonomy or a typology of battery storage technology that I previously developed based on discharge time, use case, and energy to power ratio. I have additional detailed taxonomy by battery materials and its characteristics. It's still under review to be published this year. So stay tuned for it. But let's just talk about this table that you see in the image. We can divide energy storage technologies into 4 categories based on discharge times. These categories are useful in understanding the role of the storage on the grid. There are the capacitors and the supermagnetic energy storage that can discharge enormous amounts of power, but only for a short time. Energy storage with the highest power density and lower energy density. These technology can provide instantaneous frequency regulation services to the grid. Again, they can take the role of a generator that respond quickly to the instantaneous change in electrical demand. Also, there are battery storage type that can discharge energy for a long time, but cannot provide massive amounts of power immediately. And these are the technologies with the highest energy densities and lower power densities. These are useful for seasonal time shifting, storing excess generation in the summer and converting it back to electricity in the winter. In the United States, lithium-ion batteries dominate the energy storage market, accounting for more than 90% of the market share. And these, as well as the redox flow batteries, are flexible in their design. In other words, we can play with the chemistry of the battery to fit the use case. Lithium-ion are useful for power quality, reliability, and those with medium to long discharge time are also useful for load following to flatten the duck curve and hedge against weather uncertainty. They can be used for compensating the energy imbalances due to the limited predictability of wind or solar power. In addition to this taxonomy, battery storage can be classified into residential, non-residential, and utility scale storage type. Of course, this session, we are focused on the medium and the medium to long discharge time technologies in the utility scale segment. Additional classification for energy storage could be classified into electrochemical storage, as in batteries, electrical storage, as in supercapacitors, magnetic storage as in superconducting magnetic energy storage, kinetic storage as in flywheels, and chemical storage as in hydrogen. Again, stay tuned for my next typology of energy storage technology. Energy storage will enable more efficient adoption of distributed energy resources that will help us reduce carbon emissions and support our transition to clean energy future. Utilities are mandated to increase the renewable portfolio standard by governor's executive orders. I just wanted to bring to your attention that the integration of renewable assets poses a number of challenges and opportunities at the same time. So if energy storage in specific is implemented incorrectly, it may negatively impact ratepayers by increasing costs and decreasing grid reliability. So battery system must be integrated and operated in a safe and a reliable manner. A number of tests are currently being conducted by utilities to test the impact of battery storage systems on the network. Utilities have tested peak shaving, voltage regulation, spinning reserve, and other services offered by batteries. The takeaway from my presentation or webinar last year, if you remember, is that battery storage locations can be assessed geographically to improve the reliability of the electric power network. I definitely still think that a common decision-making framework for battery storage deployment to be shared by all utilities is essential in the domain. The third class of benefits is around the energy storage that is being looked at as enabling technology necessary in the smart grid environment. The future of distributed storage will play a major role in the smart grid development. The size of these systems and their point of deployment in the grid will depend on the unique requirement on a case-by-case basis. Batteries in substation, for example, may allow portion of a network to function as an island power system. Again, islanding is about splitting the electricity network into fragments that are able to self-sustain their internal power demand. At the distribution level, microgrids may be considered as the islands of a management procedure. The ability to island is of a great benefit because the power restoration process is usually time consuming. So islanding creates the ability to have the utility customers served by a local source while the restoration effort is ongoing. Also, as we have mentioned in the previous slides, frequency regulation via drop control response reduces integration challenges associated with wind and solar generation. So we can make a statement that coupling wind or solar generation and storage will drastically increase the reliability of the grid, enables more effective network management, and creates a dispatchable power product from resources at grid operators' fingertips. The rapid response characteristic of energy storage makes it valuable asset, especially as it can compensate for the variability of the intermittent generation from solar and wind. On the transmission side, benefits will include decreased transmission losses and reduced transmission congestion, as you can see in the green section of the circle on this image. If you're looking at the big picture, we can build a holistic decision support system solution that address and predict renewable energy generation from solar, wind, and other sources add energy storage as an element here, we can develop models to yield accurate forecasts for energy demand from residential, commercial, and other use cases, tie all those pieces together to build an application that address utilities needs, aid in all types of DER portfolio choices. This is just a research framework that is still under development to provide a solid foundation to equip researchers with key information to provide direction for future research within this domain. So prospective authors in this space could examine topics such as modeling battery behavior, planning energy storage backup for the smart grid, battery data management and pipeline to enable analytics, recent advances in battery technology, the future of grid storage solutions, and advanced design to integrate energy storage into the electricity system. I would like to end this talk by giving you an update that the total amount of utility scale battery storage brought online to the US as of the year 2020 has almost been 7 times as much as developers completed in 2019. Battery storage in the US has grown tenfold in just 5 years, and its growth is only accelerated. President Joe Biden and Gina McCarthy, who Biden has tapped into his national climate advisor, recognized the storage as a critical or central component for building the grid systems. Batteries can reduce the need for less efficient, dirtier peaking plants that can be brought online to meet demand at high usage times. Energy storage can make a variable power resource more consistent. In the next 3 years, more than 15,000 megawatts of utility scale storage are planned to enter service per the S&P Global Market Intelligence data source. The takeaway is that battery storage technology can help contribute to the overall system reliability as wind, solar, and other renewable energy sources continue to be added to the grid. Storage technology will be an effective tool in managing grid reliability, again, by regulating generation fluctuation and improving the grid functionality. It will provide redundancy options in areas with limited transmission capacity, transmission disruptions, or volatile demand and supply profiles. Utility scale storage can be instrumental for emergency situations because of its ability to provide backup power as well as grid stabilization services. It is expected to help the state utilities avoid the need for load shedding. It will provide the ability to dispatch to the power grid when electricity demand rises, which is often when the sun is setting in states like here in California. With that, I would like to end this session. Thank you for your time, and let's see if you have comments or questions. All right. Anybody has questions?
Dr.
Okay, I
Sultan,
see some
yeah, there
here.
are some
Right,
questions on the Q&A.
right. I could see them. Let me. So there are 4 or 5 questions. The first one is, has the pandemic impacted the development of energy storage systems in the US, and what is the situation in California? I would say that progress on clean energy technology has been really been promising. We are doing good. However, renewable growth slowed down a little bit in 2020. We saw some delays in construction due to supply chain disruptions, lockdown measures, social distancing guidelines, and emerging financing challenges. However, most of the planned utility scale projects came online on time. I would say that it's mainly the installation for businesses and households that were depressed, especially those without strong government support. In California, to be specific, we need as much as 15,000 megawatts of battery storage capacity to reach the carbon-free grid by 2045. Kaizo Grid currently has about a little bit of, about 900 megawatts. As all planned projects came online on time. The largest battery resource in the country was connected to Kaizo Grid, adding 62.5 megawatt of storage. Additional 1,000 megawatt of storage capacity is scheduled to come online over the next couple of years. Many of these projects, I would say, already have been contracted, and a good example is the Gateway project. So I would say that we have done well in spite of the coronavirus epidemic and the slowdown and the challenges that we had in the supply chain.
Dr. Sultan, I have a quick question.
Sure.
Can you talk about the battery storage types and provide more detail regarding how these types are useful in understanding the role of storage on the grid?
Yeah, sure. So as I mentioned in the previous, in some of the slides that I showed you, we can divide energy storage technologies into 4 categories based on discharge times. These categories are useful in understanding the role of the storage on the grid. So there are the capacitors and the supermagnetic energy storage that can discharge enormous amounts of power, but only for a short time. And these are the energy storage with the highest power densities and lower energy densities. These technologies can provide instantaneous frequency regulations and services to the grid. They can take the role of a generator that responds quickly to the instantaneous change in electrical demand. There are also other battery storage types that can discharge energy for a long time, but cannot provide massive amounts of power immediately. And these are the technologies with the highest energy densities and the lower power densities. And these are useful for seasonal time shifting, again, storing excess generation in the summer and converting it back to electricity in the winter. In the United States, lithium-ion batteries dominate the energy storage market, accounting for like 90% of the market share. And these, as well as the Redox flow batteries, are flexible in the design. We can play in the chemistry of the battery to fit the use case. Lithium ion are useful for power quality, reliability, and those with medium and long discharge time are also useful for load following, again, to flatten the duck curve and hedge against weather uncertainties. I don't want to share additional taxonomies or typology, but again, stay tuned because there is a publication coming out this year with a new typology of battery storage systems.
Dr. Sultan, I think Errol has a question. He says, who is the world authority in renewables?
I would say the customer. The customer is the one who has the authority in everything. We try, and utilities, state developers are trying to meet the customer demand or needs. So if customers think that renewables are good for the environment, they think that these are good source of, they could replace the coal plants, the dirty coal plants, that they are reliable, that they are a great investment for the future, then that's the direction we're going.
Thank you. I think the next question is, how much has the pandemic affected the current state of grids?
And I think I would say that the pandemic, the electric grid was able to meet, I would say throughout the entire year, we have seen how reliable was the electric service to customers. It just, the only, I wouldn't say that it impacted the reliability as much as it impacted the way we consume energy. So now I think we have more consumption or usage from residential customers throughout the day versus before we used to, people, the duck curve was really, I would say, more, we were not at home during the day. The consumption curve was looking different than the way it is with the pandemic today. So I would say that we have done pretty well. We all have electricity. We're all working from home. There is minimum disruption. I'm just, I'm very proud, in spite of all the challenges that we may have had in the last couple of years, but I see that we are going in the right direction.
The next question is, how much can storage and microgrids act as a disruptor to establish energy grids?
I wouldn't say it's a disruptor as much as I would say it's enabling technology. I like that word when it say it's enabling technology. So it will enable renewable, it will enable reliable service. Yes, it's you could look at it as a disruptor, but I would say a good disruptor. That's going to be part of our new norm, is having a storage system with our, in addition to the solar panel, if we're looking at a microgrid, utilities are going to be relying on storage system to meet demands in peak times. So it's a good disruptor. It's I would say it's an innovative technology. It will enable the new grid that we are trying to build for the 21st century.
JB is asking, is your research primarily focused on the US energy grid and utilities? What other parts of the world would your research benefit?
No, my research, anybody can benefit from my research, because if you look at what we're doing here in the US, it's been replicated in other countries in other parts of the world. So in fact, I'm very proud to be from California, considering all the accomplishments that we have done, especially within the energy storage applications, within within the energy domain in general. I would say that so all the models that we have developed, all the tests that we have conducted here in California or in the US, people in other parts of the world can definitely still benefit from that. The intention of research in general is that we contribute to knowledge. We are trying to add new knowledge. That is why we do research. So if once we complete a research and it gets published, other people in different locations in other geographic area can definitely apply the findings, of course, in their setting and using, their data.
Catherine is asking, is the same technology being applied to electrical cars?
The electrical cars, so the electrical cars use battery. Yes, so it's the batteries. Most of the Tesla, for example, if you look at Tesla batteries, these are all lithium-ion batteries, which is what we know for now. And for those of you, the lithium-ion battery is just how we can pack a lot of energy storage in a small light battery, making them the battery of choice. Not just in an electric car, but we can even, and that's what we use in small electronics such as laptops and cell phones. Yes, battery storage is what we use. It's the same technology. These have short, the only challenge with them is that we have a short operating life and have issues such as rapid heat generation. However, again, we are continuing research to improve that, the shorter lifetime associated with these batteries. We have seen a drop in the battery cost. Within the utility scale segment, there are other types, not just the lithium ion that has been used. So we've seen, for example, the flow batteries, that is like 2 tanks of liquid, which simply sit there, and when pumped into a chemical reactor, the two solutions flow adjacent to each other and generate a charge by moving electrons back and forth. So this type, the flow batteries, this battery offers unlimited energy capacity. There are other types beside lithium ion. I would say in electric cars, mainly the lithium ion batteries dominate the section. That's the only difference.
The next question from Manuel, as the events showcase the snow in Texas, shown some potential issues for the grids in certain states and areas. Is there a need to better reform some areas?
That is a big subject. I don't think we have time to discuss what's going on in Texas right now. I would want to, talk about it in another session. But again, these, as you have seen in the taxonomy that I offered, the types of the power failures, I would say that though there are a number of reasons contributed to the outages in Texas, but I would say that yes, the ice storm was the main contributor, and that is the factor. So if I am classifying Texas outages and reliability issues, in my opinion, these should be classified as environmental related outages.
Thank you. Dolapo asks, how much focus of solar or wind energy generation with battery storage is tied to the grid?
I'm not sure I understand. How much focus of solar or wind energy generation?
Yeah, with battery storage is tied to the grid.
I would say battery storage is considered a renewable energy resource that could exactly like a solar or wind, because it discharge power or offers power to the grid when it's needed. So I would say that in the future, I see, especially with the battery storage pricing dropping, I would see more utilities and customers relying on batteries to complement what the wind and solar generation can offer. So the thing is, during the day, when there is a lot of possibly, for example, solar energy generation, sometimes instead of giving it back to the grid, you can save it in your in battery of your electric vehicle, or in your residential battery storage, so that you are more independent. You are not as reliable and you're not so that you are self sufficient in terms of you can generate your electricity, store it, and then use it later when you need it. This is with respect to the microgrid. For utilities, utility grade storage, I would say it acts again as a resource that can offers it's a resource that can provide electricity when needed, in case there is it's a time of a peak demand, or there is some kind of an emergency for an additional need for electricity.
Catherine is asking, what challenges are you having with protecting users from cancer over long periods of time? I'm assuming this is to do with the grid side of things.
I'm not aware. I'm not aware that there are cancer issues over. I only know that there are people are exposed to cancer if they have like a power pole in front of their house. That's the only time that I've heard of people concerned about this. When it comes to, again, the renewable, I think battery storage, I am not aware that there are any risks or threats or any concerns about getting, cancer or so. I'm sorry that if there is something, but I am not aware of that.
Thank you, Dr. Sultan. The last question is from Joshua. Would the principles of supply chain management coupled with big data be a good approach to analyzing the new dynamic in the future energy grid, which flows in multiple directions?
Yes, definitely. The principles of supply chain management coupled with big data is a good approach to analyze the new dynamics in the future energy grid. And as I mentioned, there are models that are being tested right now to, for example, to optimize locations of renewables, to do models to calculate or to do the capacity analysis of a circuit line, and a lot of models that need to include or to consider the demands coming from residential, commercial, and other places, and at the same time considering all the sources of supply, tie all of that together, and do calculation in real time, so that customers and utilities, both of them, can make decisions, sound and good decisions, so that the reliability of the electric power network is not impacted, and so that we're going in the right direction.
Thank you, Dr. Sultan. So I think that's the end of the questions. Thank you all for participating in this webinar. As I said, the recorded video will be on our YouTube channel, and the slides will be posted on SlideShare. Our next webinar will be next month. Please watch out our emails for information on that. It'll be a fireside chat with the venture capital. We hope to see you then. Thank you once again. Thanks, everyone.
Thank you, Sabash. See you later.